I'm going to speak about Djikstra algorithm. It's a simple and practical algorithm that is used to find the shortest path between two nodes in a given graph. In this video, we are going to see what the shortest problem is, how Djikstra algorithm works, a step-by-step example, and some real-world applications, and along with a quick summary. The shortest path problem is like this. Imagine you have a map. Cities are connected by roads. Each road has a distance, and you want to find the shortest route from one city to another, and that's exactly what the shortest problem is. So you have to consider cities like nodes, and each road as a edge and distance as the weight of the graph. But the thing is, Dijkstra algorithm only works when the graph has positive weights. Dijkstra algorithm was invented by Edgar Dijkstra in 1956. It's a greedy algorithm, which means it picks the next best option in every single instance. It works when all road distances are positive, and basically it finds shortest path from one point to another by comparing the distance between current node and the destination node, and compares it to the minimum value and updates it in a permanent list. To do this, the algorithm keeps track of three things: a list of shortest distances, which is basically calculated at every single node. The nodes which can't be reached from a node is basically assigned infinity. A set of nodes that are already finished. Once we finish a node, we don't change it because it will be a minimum distance. A priority queue, that's just a way to always pick the node with the smallest distance next. Basically, that's only needed if you're going to implement the algorithm in some coding languages. Set the starting point to 0 and all others to infinity. While there are nodes left to process, pick the unprocessed node with the smallest distance, mark it as unprocessed, means mark it as infinity. Look at its neighbor. For each neighbor, calculate a new distance, and calculate the distance from the current node to the destination node, or check if the distance from the starting node is already lesser than the current calculated distance, and update it accordingly. When we are done for every single node, we can finally find the shortest distance from one node to every other node. Basically, this is the algorithm Google Maps use. There's also a similar algorithm, Bellman-Ford algorithm. We'll talk about it later. And here is the simple pseudocode for the Djikstra algorithm. Here we initialize this stuff source equal to 0, and every other node which is not the source node we are taking as infinity. While each node remains, we compare it with the neighboring nodes and then calculate the distance, and then pick minimum distance for each node and update neighbors accordingly, and do this for every single node, and then you can easily get the shortest path from source to destination. And here are the data structures that can be used to implement this algorithm. It's basically arrays or list, graph representation. Basically in graph you can represent as an adjacency list, which is a 2 by 2 matrix in Python or any other coding language. And then priority queue. In adjacency list, you assign the nth row of the mth column as the weight of the graph. So you know that this node to from n node to the mth node costs this much weight. And the time complexity of this algorithm is O v square. V is the number of vertices, and E here is the number of edges. And if you use min the time complexity is O v plus E log v. But basically we are using array and matrix most of the time. So here's an example graph. Consider nodes A, B, C, D, E, edges A to B as a weight of 2, A to C as 5, B to C as 1, and B to D as 3, C to D as 2, and D to E as 1. We want to find from A to E basically. So we'll start at A we assign 0, and since B and C are neighboring nodes, we assign B equal to 2 and C equal to 5. Now we go to B, which is the next neighbor of the A, and we go here and we see that C and D are connected to B. So we check the distance from B to C and D, which is 3 and 5. So we are going to update the distance to C and D as 3 and 5, because That's the minimum length we have from A to that current node till now. Now we are going to C, which is the next neighbor. We can only reach D from C. So since the path still takes the distance as 5, we don't really change it. And now finally the D's neighbor is E. So from A, but then to D, then to E, we can easily reach E at uh, distance of 6. So here are the final shortest distances: A equal to 0, and then finally you can reach E equal to 6. Basically, with 6 distance, you can reach from A to E, which is the shortest path for this problem. Now this is the shortest path. We have to traverse from A to B, then to D, and then to E. The total cost is 6. Basically, to visualize this, we use diagrams like I showed before. The diagrams with nodes and edges, and with its weight marked in every single time in every nodes. So we can use this Djikstra algorithm in navigation system, basically in ships or something, in even vehicles. And network routing, OSPF uses this algorithm to locate the next network. And then robotics and games we can use. Basically in games, it's for pathfinding for the NPCs. So basically if an NPC is walking through a city, and if some obstacle comes in between, he has to find the next shortest path to reach his destination, considering that the current node has been severed. In computer networks, we use this algorithm for routing algorithms like OSPF as I mentioned, and then find shortest path for data packets. In datagram approach, each and every packet moves from source to destination as it finds the best path. So this is how it finds the best path. And then the OSPF full form is open shortest path first. As I said, it uses the Djikstra algorithm. It the routers compute the shortest path tree from the source router to the destination router, which enables efficient data transfer. In networks, each router is considered as a node, each link as a cost, which is basically the bandwidth and delay, because in networks bandwidth and delay or like the time taken to reach from one to another, like we have multiple delay, transmission delay, propagation delay, and processing delay, and etc. So we have to keep everything in our mind and calculate the cost, and Dijkstra allows us to calculate the best path. The advantage of this is it calculates the accurate shortest path every single time, even though it's a greedy algorithm. It's not efficient for negative weights, so you can only use it for positive weights. It's applicable in mostly in real life, because in real life you are not going to have any negative weights, only positive or zero weights. Limitations is just that it cannot handle negative weights, and you need such a large memory to compute for large graphs. Like imagine having 100 nodes and you have to calculate adjacency matrix for everything, and you have to calculate the next neighbor and all those things. It involves so much processing power. So that's really its only limitations. And comparing this thing to Bellman-Ford algorithm, sometimes Dijkstra is faster than Bellman-Ford algorithm, but the advantage is Bellman-Ford can handle negative weights. Real life example is, as I said before, Google Maps can use Dijkstra algorithm to calculate shortest path. Now I'm going to explain about difference between Dijkstra and Bellman-Ford algorithm. In Dijkstra, the algorithm assumes that once a node is finalized, or basically when it's processed, the values cannot be improved later, and it removes from the priority queue. But this cannot work for negative edges, so Dijkstra violates it. Whereas in Bellman-Ford algorithm, it relaxes every single edge v minus 1 times, where v is basically number of vertices, and this guarantees that the shortest distance are found no matter what. So basically Bellman-Ford and Dijkstra finds the shortest path, so both the shortest path algorithm, but Bellman-Ford has more overhead, but still it can calculate the negative weights, and shortest path when negative weights are present in a graph. So that's its only advantage. And then Djikstra is a greedy algorithm. It processes every single node in the order of increasing distances. It's like shortest path tree outward from the source. Bellman-Ford algorithm uses dynamic programming. It iteratively improves distance estimates by considering all edges. It's like uh, propagating information to the graph. Performance-wise, Djikstra is way more faster because Bellman-Ford has to visit every single vertices and it has to relax it. So it's not really used for where there's no negative weights. Uh, so basically, when choosing an algorithm, choose Dijkstra if you know that there won't ever be negative edge, or else choose Bellman Ford if you know there will be negative edges. The time complexity for Bellman Ford is basically O Vx V into E, where E is the number of edges, and this because it has to visit every single vertices V minus 1 times. So Dijkstra is mostly preferred for most computations. And now let's see a simulated version of Dijkstra algorithm. Here, as you can see, the nodes 0, 3 and 4 are disconnected from the graph. So in the end, all these nodes should be unreachable from the node 1. We are going to check from the node 1 from here. We want to find the shortest path from node 1 to every other node. So let's run the simulation. This is so you can start from 1, and now let's check the next neighbor, which is 2, 5 and 6. So from 1 to 2 it's 4, and from 1 to 6 it's 3. So we are going to take the next neighbor, which is 6, and we're going to check every other neighbor, and we are updating the distances here. As you can see, from uh, node 1 to 2 we are getting 4 as the smallest distance, where you can even verify from the graph itself. And now the known column of this graph means if it can be reachable or not. As you can see, the cost 0 is still at infinite because you can't actually reach it. So since there's no path from 1 to 0, we are putting -1 there. And as you can see, then the vertex 1 can be reached by itself just to path 1, so it's just there. To 2 you have to reach from 1 to 2, and then for 5 similarly 1 5, and then for 6 1 6. For 7 you have to reach from 1 to 5 to 7, which has a distance of 10, and you can even verify from the graph that it's the smallest path. And in the end we can see that vertices 0 3 and 4 as cannot be reached, so it's just at infinite distance and path as -1. Since Djikstra consumes so much space and time, there are some optimization for Djikstra, which are basically some new algorithms which just modified Djikstra. So the first and most basic one is bidirectional Djikstra, which runs from both source and target simultaneously. So it will stop when two of the searches meet one common node or even multiple common nodes, and then we can check the smallest number of smallest distance, and then by this we can reduce the number of nodes visited and the time needed to process significantly. So basically it's like Djikstra divided by 2. And then next one is A star algorithm. A star adds a heuristic estimate to the remaining distance of the node and target. Like it guides the search towards the target, and it's much faster for point-to-point queries. Essentially, Djikstra with a modified priority. It assigns priority to each node, so it can only be used in certain cases. And next one is the counteraction hierarchies. It's a pre-processing techniques that removes nodes and adds shortcuts. Queries then run bidirectional Djikstra. So you need pre-processing power for this, so it's not widely used. And then there's the dynamic and incremental Djikstra. When edges weights change, rerunning full Djikstra is expensive. So Just we have to rerun on the places or the parts that include the weights that actually changed. Something like this can be used in Google Maps for traffic, traffic detection, and to calculate new part easily. And now I will speak about Djikstra's role in routing protocols, basically OSPF, which is Open Charters Part first. There are two major interior gateway protocols. Routers exchange information about link costs like bandwidth delay, like because that's what's considered distance or weight of edge in this case. And each router runs Dijkstra to compute the shortest path from that router to every other router in the graph. The result is used to populate the forwarding table. Because networks change, OSPF runs Djikstra repeatedly. But since we saw that running it repeatedly is inefficient, the above optimizations could be used instead. But a graph size per router is typically manageable, just thousands of nodes. The algorithm, it determines and ensures that there are no loops in the route it takes. And then there are a few variants for in this algorithm, which is Dial's algorithm. Basically, when edges are just small integers, we can use bucket based priority instead of an heap. Basically, in heap is like a binary tree. There are two types of heap, min heap and max heap. So basically, min heap has the largest node on the top and the others below, and max node has the smallest on the top and the largest below, like on the leaf edges. So in this case, when C, which is the maximum edge weight, can be assigned an higher priority, and max heap can be implemented in this case. Next is multi-criteria Dijkstra. It finds paths and multiple objectives. Often, it's solved by the lexicographic ordering. So, but this starts so much overhead, so we can't use it oftenly. And then there are k shortest paths. Repeatedly runs Dijkstra and adds deviations to generate alternate routes. The limitations and alternative that you have to choose when encountering Dijkstra is when there's negative edges, you use Bellman 4, or if there's negative cycle, use the SPFA algorithm, and if all paths shortest paths, you use Johnson's algorithm, or if it's an unweighted graph, which means every single edge has equal weight, or you can consider it as one, use breadth first search or depth first search. For very large and static road networks, we can use Dijkstra itself or with some of its optimization. So that's all about the Dijkstra algorithm. We visited some of the examples, and I explained about some of the alternatives and more optimizations in Dijkstra algorithm. So thank you.